All right. So welcome back. And today, this is one of the last two classes on Laplace transform. So this was mostly a recap of Laplace transform. And so today and on Thursday, on Friday, we are going to discuss the different properties of Laplace transform and how we shall also discuss how we actually use them for control system. So for analyzing and designing control systems mostly. And we are going to talk about different properties of Laplace transform today. And some of these properties have already been discussed, the rather important properties of Laplace transform. Of course, the properties like the convolution property and the time derivative property have already been proved. We have already elaborately derived all those properties, right? So we are not going to derive them with those elaborate details today. At least we are going to skip the convolution part because we already derived that convolution part in our last discussion, I think. So we are going to skip that part, right? But about the time derivative, we are going to derive that today, and we are going to tell you certain things about it which we did not discuss in our class on transfer functions. So again, whenever you have any query during the class, feel free to ask. I shall be definitely answering your queries. And as you already understand, that Laplace transform is one of the fundamental building blocks of classical control systems, right? But I'm saying classical control system because nowadays, I mean, of course, Laplace transform has got quite a few limitations, and we're going to discuss those later on in due time. You will see that, I mean, it is good when it is applicable to the systems we are discussing. But many times we would see that applying Laplace transform is not possible, or even if it is possible, it might be inconvenient to some extent for certain types of systems. So we're going to see those, and we're going to figure out a way of kind of skipping Laplace transform when it is really necessary to do so. And we would have different insights on the same types of systems using other mathematical tools. So the point being, in around in 1940s, 1950s, in those decades, people are working on different things all at the same time. Some of those special people were working on designing amplifiers. Some of them were designing certain electronic circuits. Some of them were designing automated mechanisms. And whatever we are studying today, we are studying the essentially the culmination of all those discoveries that the scientists made back in those days. Right? And we have to understand that back in those days, people did not have computers, okay, let alone a calculator, right? So every computation was done manually, and because of that, the methods and algorithms and mechanisms, things that the scientists and engineers developed back in those days revolved around making the lives of engineers easier, right? So again, the computations that we are going to learn throughout this course can be done without a computer, without a calculator. So essentially those calculations we would be able to do those calculations without using a calculator, because that was the point back in those days, right? But in any case, nowadays we have a computer, so we have computers, so we can use what should I say, take the help of computers for our computational needs, right? In any case, so let's start our discussion. And again, we are saying Laplace transform properties, and as far as I recall, I told you the definition, I mean, we derived the definition of Laplace transform as an extension of Fourier transform, right? As an extension of Fourier transform, and we derived it as an extension of Fourier transform again. So I cannot emphasize this enough that Laplace transform is essentially a special kind of Fourier transform, rather a modified version of Fourier transform, right? So Laplace transform of a signal xt is essentially the Fourier transform of the signal xt multiplied with a certain exponential factor like that, where sigma is a real number, okay, and this is known as the Laplace transform of xt. So essentially that is the definition. All right. So again, our definition of Laplace transform is this one. So we say xs is the Laplace transform of the signal xt if we calculate this integral on xt, and we derived all these things. And what is this sigma, what is this s? S is essentially sigma plus j omega, right? Where sigma is this factor, okay, and of course j omega actually came from the Fourier transform itself, right? So that's the definition that we have been using so far. All right, I think there is no issue with this, right? So now what is S? Of course S is sigma plus j omega, right? So let's write that. So with this line I can write this is x sigma plus j omega, and that's equal to integration like this. So this is xt e to the power minus sigma plus j omega t, and here we have dt. All right. So again, during the class, if you have any query, feel free to ask. I shall be definitely answering your question. Okay. All right. So that's understood, and there is no issue. So again, let me just split this part a bit. So this is the Laplace transform. So instead of S, I'm writing this. And this is e to the power minus sigma t. So again, hold on for a second. So this is e to the power minus sigma t into e to the power minus j omega t, right? We just split the power of the exponential like that. So this will be minus sigma t minus j omega t, and accordingly this is the split. And of course we can write it this way, right? That's not an issue because we're just multiplying things. So essentially, what is this? The right hand side of this is essentially, this is nothing but the Fourier transform of xt into e to the power minus sigma t. If you recall the expression for the Fourier transform, so this is essentially the Fourier transform of xt into e to the power minus sigma t, right? So this is xt into the power minus sigma t. So if this is your function, then if you are multiplying that function with e to the power minus j omega t and integrating from minus infinity to plus infinity with respect to t, you are essentially getting the Fourier transform of this, right? So essentially this x sigma plus j omega is this one. Now again, this is nothing new, we have seen this already, right? We have actually used this the very idea to derive the expression for Laplace transform. With that said, what we can say, let's use the notation that we used earlier. So we have the Fourier transform of xt, the Fourier transform of xt e to the power minus sigma t, that's equal to, so we have the Fourier transform of xt e to the power minus sigma t, that's equal to x sigma plus j omega. Now my question is, then what is the inverse Fourier transform? What is the inverse Fourier transform of x sigma plus j omega? Question is, what is the inverse Fourier transform of x sigma plus j omega? We just said that the Fourier transform of xt multiplied by e to the power minus sigma t is x sigma plus j omega. Then what is the inverse Fourier transform of x sigma plus j omega? That's of course would be this signal. So essentially the inverse Fourier transform would be this one, right? Right? And that's not an issue, I think, right? So let's write this. Now what is the definition of inverse Fourier transform? So you people know already that if I have the Fourier transform, so this was the Fourier transform of something here at this point, and if I multiply this with positive j e to the power positive j omega t and integrate it with respect to omega from minus infinity to plus infinity, we derived all of these things starting from the definition of Fourier series, and we also derived Fourier series. So you can go back to those classes, right? So that's the definition of inverse Fourier transform, if you recall, right? And right, so that's the inverse Fourier transform, and that would be equal to xt e to the power minus sigma t, right? Right? So I don't think there is any issue with this, right? So we're just writing this line out. So we're just using the definition of inverse Fourier transform and expressing this way. So that right hand side remains. So in the right hand side we have xt e to the power minus sigma t, right? On the right hand, so hold on, it's also showing me some errors. Anyway, fine. In the right hand side we have xt e to the power sigma minus sigma t. So let's multiply both sides with e to the power sigma t. So if I do that, then I would have 1 by 2 pi into e to the power sigma t. Okay, and this integration I'm writing essentially. Okay, and integration from minus infinity to infinity. Okay, x sigma plus j omega e to the power j omega t d omega, and of course this is equal to xt, right? So instead of writing it on the right hand side, let me write it on the left hand side, right? So we just multiplied everything with e to the power sigma t. So e to the power minus sigma t will get multiplied with e to the power plus sigma t, and it will become 1. That's why we just have xt, right? Now look at the right hand side here. We have 1 by 2 pi, that's fine, and then we have e to the power sigma t, right? And we have e to the power sigma t that will, this is entirely made up of things that are independent of omega. Look at the integration here. This integration is being done with respect to omega, and this function e to the power sigma t is made up of things that are entirely independent of omega. So this term actually, this e to the power sigma t, can go inside the integration, right? Just as a constant. Okay, constant with respect to the integration itself. So I'm writing integration from minus infinity to infinity. I'm just pulling this term inside and I'm bringing it next to e to the power j omega t. So I'm writing it x sigma plus j omega and writing it as e to the power sigma t into e to the power j omega t d omega, and that's your xt, right? All right, so this is 1 by 2 pi integration from minus infinity to infinity, that's x sigma plus j omega, and here we have e to the power sigma t multiplied by e to the power j omega t. Just we can combine them and make them e to the power sigma plus j omega t and d omega, right? Right, we can write that. And here after this line, so this is again, this is the expression for xt. And after this line, let's do a substitution. Let's substitute sigma plus j omega equal to by s, right? So let's substitute sigma plus j omega by s. Of course, that is the definition of s. And with that substitution, we shall have to do this. Okay, let's differentiate both sides. Sigma is a kind of a constant as far as omega goes. So this is going to be j d omega equal to ds, right? And thus d omega would be 1 by j ds. And what about the limits? What about the limits of omega and s? Now look very carefully. When so the limits of omega, so omega is varying from negative infinity to positive infinity. So when omega is negative infinity, what is the value of s? S would be so when omega is negative infinity, so when omega is negative infinity, the value of s would be sigma minus j negative infinity, sigma plus j negative infinity, like that. So like that. And when omega is positive infinity, then the value of s would be sigma plus j positive infinity, right? With this substitution actually we can write something important here. So this is going to be 1 by 2 pi. So the limits now change to this, right? Sigma plus j infinity. That's the change of the limit. And now this is becoming xs. This is becoming e to the power st. And instead of d omega, we are going to write 1 by j ds. And 1 by j is a constant, so we can bring it outside. We can write it as 1 by 2 pi j, right? So that's your expression for xt, right? All right, so this expression, this very expression here that we just derived is known as the expression for the inverse Laplace transform. So if xs is the Laplace transform of the signal xt, then xt can be calculated, or xt can be recalculated using this formula, right? So if xs is the Laplace transform, then xt is the inverse Laplace transform, and this is the integration for inverse Laplace transform. Now you probably haven't seen this expression being worked out in your mathematics classes, right? Because this, I mean, doing this integration requires quite a bit of knowledge of complex line integral. So this is essentially a complex line integral, and this would require quite a bit of knowledge of complex line integrals, right? So we do not really we won't really jump into this, and for essentially this is very complicated, right? So I mean, doing this, so if I give you the Laplace transform of something and ask you to find out the original signal, essentially if I ask you to do inverse Laplace transform, you are very unlikely to directly use this expression, because I mean, directly using this expression would require a lot of knowledge of complex analysis, right? Not only that, the calculation is going to be cumbersome. So this is so this formula is rarely used, simply because this is too complicated for at least an undergrad to actually calculate directly from out of this. But if you are talking about computers can kind of handle this if you apply proper algorithms and all, right? So again, for human beings, I mean, directly applying this formula, at least for undergraduate engineers, I mean, this might not be okay, that's an integration, and I can tell you what this integration means, but for this course I'm going to skip this. But if you say, for example, if you want to see a few examples, for example, if you just for example, if the Laplace transform of ut is 1 by s, I can show you how you take this and do this integration, okay, and ultimately get ut back. Okay, I can show you that, but for that portion I would need another class, completely a optional class. And if you are, if I mean, about like 5 or 6 of you are interested, let me know. I will arrange a special class, completely optional, and if you are interested about complex integrations like this, we shall do that. But for the most part, we are going to skip this integration here. Okay, so again, and this is pretty much recommended to skip this integration, at least for undergraduate students. But again, if you're interested, if enough students are interested, like at least half a dozen would do, then I can arrange an additional class for this. Actually, if you are doing a master's degree in control system engineering, you might at some point need to do this integration. Okay, I know I did. Anyway, so let me know, because I won't be explaining this any further. Just understand that this is simply an integration, right? There are so many things about this. Okay, so what we have essentially derived today was the definition of inverse Laplace transform. All right. All right. So that's fine, right? So now today's agenda. So we are now going to derive certain properties of Laplace transform, right? Of course, one of the first and foremost properties is that Laplace transform is linear, right? So linearity. I mean, this will be completely, I mean, very reminiscent to, rather quite similar to what we did with Fourier transform. Laplace transform is linear, and I'm not going to explain this. I mean, this is very similar to Fourier transform. So the point is, if the Laplace transform of xt is xs and Laplace transform of yt is ys, then the Laplace transform of axt plus byt would be axs plus bys, and you can just check this quite similar. I mean, this will be absolutely similar to what our Fourier transform, the way we derived it with Fourier transform. So now I'm not wasting time by deriving this, right? This is quite obvious. Okay, all right. So where a and b are constants independent of time, right? So right, so that's fine. We're not going to derive that. All right. So now the next expression we are going to derive. So of course, let's take a few examples with this. Okay, example of linearity. Say we know, for example, the Laplace transform, we know Laplace transform of, say for example, sine at ut is essentially a by s square plus a square, right? So then, using the linearity property, the Laplace transform of, say for example, 5 sine at ut would be, of course, 5a s by s square plus a square. I mean, this is as simple as it gets, right? Also the Laplace transform of, for example, some of you already did probably, the Laplace transform of cosine at ut is s by s square plus a square, right? And thus Laplace transform of sine at ut plus cosine at ut, that's going to be a by s square plus a square plus b by s square plus, sorry, a by s by s square plus s square. So that would be simply s plus a by s square plus a square. I mean, this is as simple as it gets, right? All right. So with that said, let's jump into the next important property, right? I mean, linearity is literally the most important property. Okay, but that's quite trivial here in this scenario. Okay, let's now look at time shift. So what we are looking for here is that if the Laplace transform of xt is xs, we are looking for the Laplace transform of, if the Laplace transform of xt is xs, then here, okay, yeah, sure, there was a what should I say, I am not typing anything, so it's not a typo, right? So it's a typo probably. So we are looking for the Laplace transform of xt minus a. So again, it could be xt plus a, xt minus a. Again, pictorially, so for example, hold on for a second. Say this is your signal xt, okay, and for which you probably know the Laplace transform. So pictorially speaking, we are looking for the Laplace transform of a shifted version, of this signal. So so essentially, say if we have a shifted version of this signal, say time shifted version, of course. Okay, so this way this signal is going to be something like x of t minus a. Okay, it could be a right shift, it could be a left shift, it could be any type of time shift, right? All right. All right, so we are going to find out the Laplace transform accordingly to that, right? Accordingly. So I don't yet know, for example, so let's derive it. Let's figure out. So we are now looking for the Laplace transform of x t minus a. So it's a time shifted signal, right? So if in this case, if a is positive, it would be a right shift, and if a is negative, it would be a left shift, right? So of course, let's use the definition of Laplace transform. So integration from minus infinity to plus infinity on xt minus a and e to the power minus st dt. And let me tell you, you actually see the application of this the Laplace transform of time shifted signal while we actually derived our expression for the Laplace transform of convolution of two signals in our last class. So, but again, we are going to derive the entirety of this expression here. So let's do a substitution. Our substitution would say substitute t minus a with lambda. So essentially what we have, t minus a equal to lambda. So of course a is a constant, so that way dt is equal to d lambda. And what about the limits? So here the limits are for t and then the limits are for lambda. T varies from negative infinity to positive infinity, and when t is negative infinity, lambda is also negative infinity because a is just a scalar constant, and when t is positive infinity, lambda is also positive infinity. And subsequently, with this substitution, we have the same limits appearing here, and this is x lambda, this is e to the power minus s, and what about t? So t is essentially lambda plus a, right? Because t minus a is equal to lambda, right? So this is going to be lambda plus a, and dt is d lambda, right? So we have that. So, and with this line we can write now, of course we can say this is integration from minus infinity to infinity, right? So e to the power minus s lambda into e to the power minus sa d lambda, right? Okay, now of course the integration is with respect to lambda, and look at this exponential here. So this is entirely made up of things that are independent of sigma lambda. So e to the power minus sa, that's a constant. So e to the power minus sa can go outside the integration, and that's going to be integration from minus infinity to infinity on x lambda e to the power minus s lambda d lambda. And now we can do a trivial substitution back. Again, we can just skip that part. So now we can do a trivial substitution and say lambda is equal to t, and subsequently with this trivial substitution everything remains the same, only the name of the variable changes. And again, this is not really necessary to write something like this, but this is just to make things simpler. So this is e to the power minus sa, and this is of course the Laplace transform of xt, right? So we have derived a nice expression. So we have derived that this is going to be e to the power minus sa xs. So we have proved that. So that's kind of a proof here. All right. Let's see some applications of this. Okay, applications, examples rather. Right. So we know that the Laplace transform of the unit step signal is 1 by s, right? We know that, right? Then if I ask you what is the Laplace transform of a delayed version of the unit step, say this one, so that's a delayed version of the unit step, right? So it's a right shifted version of the unit step. So the unit step signal got right shifted by 5 seconds. So what is the Laplace transform of that? So of course, using this expression, I know the Laplace. So here a is 5. So the answer would be e to the power minus 5s into 1 by s. That's an example. Okay, very simple, right? Okay, you people know that the Laplace transform of sine at ut is 1 by is a by s square plus a square. Now if I ask you what is the Laplace transform of sine a t plus 2 u t plus 2, something like that. Again, now it's an advanced version of the sine wave. Okay, so instead of starting at t equal to 0, it now starts at t equal to minus 2. Of course, the same rule would apply. So we essentially would have e to the power 2s, essentially, since here that shifting factor is minus 2. So into a by s square plus a square, right? So that's a simple example. Also another simple example, Laplace transform of, so that's another example. This is one example. This is one example. We know that the Laplace transform of the unit impulse function is 1. So the Laplace transform of a delayed version or an advanced version of unit impulse signal, so delta t minus a, that would simply be e to the power minus sa, right, into 1. So essentially I can just skip that. So these are a few examples of the application of the time shifting property of Laplace. Again, if you have any confusion regarding any of this, feel free to ask. Right? Right? So now the next one is the frequency shifting property. So the first property was the time shift, and those not the first property. I mean, one of the properties were time shift, and the previous one was time shift, and here we have frequency shift. Again, the same point, same question. What is if the Laplace transform of xt is xs? Now I'm asking a slightly different question. What is that function for which the Laplace transform is a shifted version? Okay, a frequency shifted version. What is the Laplace? What is the signal for which this is the Laplace transform? This is what we are asking. And again, we are going to write a proof here, but we don't know what we are trying to prove as of yet. So we are kind of finding the inverse Laplace transform accordingly, like that, right? And I don't think there is any issue with this, right? All right. So just like the previous one, now here there are several ways of doing this. Let's just say, okay, let me approach this problem slightly differently. Okay, let me approach this problem slightly differently, just to make sure that your brains do not explode. Okay, let me instead try to figure out, okay, fine, what is the Laplace transform of say e to the power, so say minus 80, rather 80, should I write 80? Okay, fine, let me write down minus 80 xt. Let me just instead do that. Okay, so let me just calculate instead what is the Laplace transform of e to the power minus 80 xt. Let's do that. Okay, so again, let's use the definition and let's calculate that. So we are trying to calculate the Laplace transform of e to the power minus 80 xt, and that will be by definition this integration. So that's going to be e to the power minus 80 xt into e to the power minus st dt. All right, and let's do the integration. Let's now bring this to the right to this side and do the multiplication. So this becomes an integration from minus infinity to plus infinity, and xt e to the power, then it is minus s plus a t and dt. All right, so now let's do a substitution. Let's say let's do the substitution. Say assume s plus a equal to lambda, right? All right, or rather hold on a second. Okay, we say s plus a equal to lambda. Fine. We're not doing any difficult thing here. Let's look very carefully what happens. So this is this integration. So xt e to the power minus lambda t. Now look very carefully at this integration, and let me recall. Let me recall the. Let me remind you that this is the definition of Laplace transform. So x of s is this integration, right? No, this was a kind of a trivial substitution. This is not a substitution with respect to the variable of integration. Okay, so this is a very simple substitution. We're just instead of writing s plus a, we're just writing that with a single name here. Okay, now look at this. Look at this very carefully and see what if I instead of s, if I write say instead of s, if I write, say for example, p, is that a problem? No, because we just gave it an arbitrary name, right? That's just a name, right? So instead of saying p, I could have called it a, if a is a variable, right? Because that's just a name. I can call it a cow or a donkey or something, right? Similarly, I could just call it a lambda, right? Because it's just a name, right? Right? Because it's just a name. Look very carefully, that's s. And here, instead of writing s, maybe I write s this way. So that's also perfectly fine, right? So what I mean is that, look at this one, look at this expression, this entire thing. What is this? This is just Laplace transform, but instead the Laplace transform variable is, instead of being s, it is now lambda, right? So this essentially is x lambda, where lambda is the modified Laplace transform variable. But what is lambda? What is lambda? Lambda is s plus a. So this is s plus a. So what we essentially have derived is that the Laplace transform of e to the power minus at xt is x s plus a. And now it has wonderful applications. X s plus a. Alright. So I think this is reasonable, right? So now applications. Let's see examples. We know that the Laplace transform of, again, sine at ut is a by s square plus s square. Question is, then what is the Laplace transform of e to the power minus bt sine at ut? So again, a decayed version of sine wave, this sine wave, right? So here, look very carefully, this was the Laplace transform. So s square plus s square, right? And this is xt here, right? Look very carefully, this is xt, and this is being multiplied by e to the power minus e to the power something into t, right? Like that. So the result will be a shifted version of the frequency. So if I have e to the power minus bt here, then this becomes x s plus b. So this s here has to be replaced by s plus b. So instead of being s square, I have s plus b whole square. All right, just like that. Take another example. Let's take another example. We know that the Laplace transform of, again, say cos at ut is s by s square plus s square. Then of course the Laplace transform of e to the power say now we are multiplying with a positive quantity. What? So e to the power bt cos at ut. What about that? So that would result into, so now here we are, so this is your xt, this cos at ut, this is your xt, right? So and we are multiplying that with this one, right? Right? So now this is that multiplying factor for which we are trying to calculate the Laplace transform of the total signal here. So again, since the multiplying factor is now e to the power bt, so the value of a would be minus b essentially, right? So imagine this to be e to the power minus at, so a is essentially minus b for this purpose actually. So with that said, all you have to do, we have to replace s by s plus a. Now of course a is minus b if we just apply the formula, so that's going to be this, right? And of course if instead of being positive here, if this is negative, then this is going to be positive here and positive here. Very simple, right? All right, let's take another example. So we know that the Laplace transform of the unit step function is 1 by s. Question: what is the Laplace transform of e to the power minus at ut? Of course now s will be replaced by s plus a, so answer is 1 by s plus a, and we actually derived this manually. Someone is saying somewhere it will be b square. Where? I think someone is saying it will be b square. No, it's fine, right? So this is also understandable, right? So again, we derived this manually, right, by using the formula and doing direct integration, right? Now by applying the time shift property, sorry, frequency shift property, we can actually get it directly, right? So that's your frequency shift property. And if you have any query, feel free to ask at this point. All right. All right. Now let's look at the time derivative property, and we actually did the time derivative property. Okay, and we shall do it once again here. Okay, again, now this is the time differentiation property. Time differentiation property. Question is, if the Laplace transform of xt is xs, then what is the Laplace transform of the first time derivative, so which is essentially x dot t? We are calculating this. So let's now again write a proof, and of course we don't know what we are trying to figure out, but we are just finding out. So we are trying to figure out the Laplace transform of the derivative of xt. So we are trying to figure out the Laplace transform of the derivative of xt. Let's apply the definition. What is the definition? This integration, right? So this is the definition of Laplace transform. So let's do that. Now here, for this particular example, I am considering a causal signal. Now what is the point here? The point being that the signals that we will encounter for our purpose are causal, right? So they are starting from a certain point. They do not start from negative infinity and such, right? So in this particular one, we are going to consider causal signals. So here, so I told you when I actually derived this during our discussion on transfer functions, I told you this derivation has got certain hidden implications, right? Hidden conditions. So one of the hidden things we are talking about here is that xt is causal. So one of the hidden conditions that we did not discuss in that portion, I said I will discuss that later. So that one of the conditions is that xt is causal, and the moment it is causal, I can reduce the lower limit from negative infinity to 0. Because for a causal signal, the value of the signal would be 0 if t is negative. Alright, now let's apply the integration by parts, right? I'm going to consider x dot t to be the second function, because that will be easier for us to integrate. because the integration of x dot t would be xt. So this is the integration by parts. So e to the power minus st integration on x dot t dt, and the limits are from 0 to infinity, minus integration ddt of e to the power minus st integration on x dot t dt whole thing dt. Okay, and of course limits are from 0 to infinity. All right, so again this becomes e to the power minus st, and this is xt. Lower limit is 0, upper limit is infinity, minus integration from 0 to infinity, and of course this becomes minus s into e to the power minus st. I can bring the minus s outside, and become, since that's a constant, because the integration is being done with respect to time t, I can bring that outside, bring this s outside and make it a plus s. So this is going to be e to the power minus st into, and what is this integration? That's just xt dt, right? So this is that dt here. All right. All right, so plus s. Now what is this entire thing? S multiplied with, this is just xt dt, xt into e to the power minus st. So this is the integration of xt e to the power minus st with respect to t from 0 to infinity. So this is essentially the Laplace transform of xt if xt is causal, right? So I'm writing xs. We assumed xt to be causal, so this is the Laplace transform, right? And here for the upper and lower limits, look carefully, we are putting the upper limit here and the lower limit here like 0, for example. Okay, so here what we are essentially trying to do, what about the upper limit here? So let's just write it down. So e to the power minus st xt, lower limit 0, upper limit infinity, right? So essentially if we write this out, so we are putting t tending to positive infinity here, so limit, so that's the upper limit, t tending to positive infinity e to the power minus st xt. And what about the lower limit? The lower limit is 0, let's put t equal to 0. So we have e to the power minus st, which becomes e to the power 0, which is 1, and we have x0, and then we have plus sxs. Again, uppercase x means the Laplace transform, lowercase x means the time domain signal. And in our earlier derivation we considered this to be 0, but now we know that this is not unconditionally 0, right? Because in one of our previous discussions we derived that now we know that this limit e to the power minus st xt, so rather e to the power minus xt, that is equal to 0 under a condition. What is the condition? That the real part of s is greater than 0. We derived this. Right? We did this earlier, right? So we know that. So essentially this is equal to 0, this portion is equal to 0 under a condition, right? Under a condition. What is that condition? The real part of s must be greater than 0. So we kind of skipped over these portions here, and we I told you in the last class that I am going to explain this when the time comes, right? So this is minus x0, so minus x0 plus sxs. So essentially what we have is that the Laplace transform of the time derivative of xt is sxs minus x0, right? And this is called the initial condition of the signal. Right? And again, what are the other hidden things about this? Xt has to be causal. Also the condition is that real part of s must be greater than 0. So these are the conditions hidden behind that. So that's the initial condition of the signal. So a special case would be when the initial condition of the signal is 0, right? So again, if you are talking about electrical circuits, The capacitors, the inductors, they are not storing any energy. So any energy storing element is not storing any energy. So the capacitor does not have an initial charge. The inductor won't have initial magnetic field established in it. So special case would be zero initial conditions. Zero initial conditions, that is x0 is equal to 0, x dash 0 is equal to 0, and so on. Under those conditions, the Laplace transform of the time derivative of the signal, first derivative of the signal would be just sxs. Okay, similarly Laplace transform of the second time derivative of the signal would be s square xs. Third derivative would be x cube xs, and as such the Laplace transform of the nth derivative of x with respect to time, that would be x to the power n, right, under zero initial conditions. Of course, I'm not going to show you any application directly right now, but you can understand that it has immense applications while we actually solve differential equations, right? So of course for a differential equation, if we apply this property, what happens? The differential equation actually converts to an algebraic equation. So this property converts a linear ODE, linear ordinary differential equation with constant coefficients, to an algebraic equation. To an algebraic equation. Essentially a polynomial equation, right? Let's forget that. It's an algebraic equation, that's fine. So that's the problem. That's the use of this. I mean, we use this property every single time whenever we are actually talking about control systems, classical controls. All right. Now, for our purpose, rather, so this is classical state. Okay. So this is what we do, right? So this is what we do as a control system engineer. Now try to understand this very carefully. I mean, this is now, we're not discussing mathematics at this point right now. So try to understand as control system engineers what we do, right? So let me just give you a very small example what we actually do, right? We look at physical systems that we want to control, right? Right? So again, if I ask you a question, who invented steam engine? Some of you might say, okay, James Watt invented steam engine, right? Not really. James Watt didn't invent a steam engine, right? He actually invented a mechanism to control the steam engine, right? The point was the steam engine pretty much created the industrial revolution per se. But question is, who invented steam engine? It wasn't James Watt. Contrary to popular understanding, actually James Watt invented a mechanism to control the steam engine, right? So if I want to put my steam engine in a vehicle, I would want to control, okay, the throttle of that, right? How fast or how slowly the engine goes, I have to control that. So James Watt actually invented a mechanism to control the steam engine, and as such, he is often called the father of modern controlling, a father of classical control engineering, right? So he invented something called a fly ball governor. Okay, you can just go to Wikipedia and search for fly ball governor. Okay, fly ball governor. Okay, and you will see how he invented a mechanism, a very elegant and nice and easy to implement a mechanism to control how fast or how slow the steam engine actually runs. Okay, because otherwise nobody will be able to put an engine into a vehicle, right? Something like that. Unless you can control how fast or how slow your vehicle goes, there is no point of putting an engine there, right? So James Watt actually invented a mechanism for that. So he is the father of classical control engineering, well, in many opinion, right? So what we do as electrical engineers, as control system engineers, we look at a system. So this is kind of the entire thought process or entire engineering process behind control system and automation engineering, right? So again, control is pretty much heavily involved in automation engineering as well. So we look at a system we want to automatically control. So we are looking at a system for which we want to develop an automatic control mechanism. So we first look at a system, right? So by looking at the system, what we would try to figure out, we try to figure out how it interacts with the environment, right? What are the internal mechanisms, right? So with that, what we develop is a mathematical model. By looking at the system, what we develop is a mathematical model, right? So if it's a mechanical system, of course there will be interactions of, so different forces will interact with different objects, right? Accordingly, if there is a spring and we apply a compressive force, the spring will get compressed, but this will also apply a force in the opposite direction. If there is a shock absorber and damper, something like that, it will absorb velocity like that. If there are frictions, we have mathematical model for that. The point being, we would try to develop a mathematical description of the entire mechanism per se, right? So if we have certain things in mechanics, for example, we're trying to figure out the mechanics, right? How it interacts. So the mathematical model. In first year, you did mechanical, you study mechanical engineering mechanics, right? So there you did mathematical modeling for mechanical systems, right? Then also you studied circuit theory. Then there you actually developed the mathematical model for electrical circuits. Then you studied electronics. What are you doing actually in electronics? The same thing. You are trying to develop the mathematical model for electronic components, right? Electronic circuits, maybe be it analog or be it digital. The mathematics might look different for different types of things, but it is still mathematics nonetheless. So what we essentially do, we try to develop a mathematical model. So we first look at a system that we want to control. So unless we want to control something, there is hardly any reason for it to study mathematically, right? Unless we want it to do something we want, we do not need to study it, right? So the point being, we want to, just let me give you an example. Really, so this was in one of my favorite movies. It says that one person was actually, say, imagine this was like a post-apocalyptic world. So everything has ended in the universe, in the world, and there was a small colony of people, right? And they're living in a hostile planet, for example, and there is an air circulation system, right? We human beings cannot live without oxygen, right? There is an air circulation system. So one of the leaders of that population was bringing the hero of the movie there, and he's saying, look at the air circulation system. This is so elegant, okay, but the point is, no one really cares about how it works, as long as it works, right? As long as it works, no one really cares about how the air circulation system works. And unfortunately, if the air circulation system somehow stops, everybody will start dying and suffocating, and then they will care about how that system works. And that's true in every aspect of our life. As long as things work, we do not really care about how things work. The moment things stop working, we start caring how things work. Really, the point of this is that we want to make things work the way we want them to. So we kind of want, I cannot tell you the name of the movie, right? So the point is that we are kind of looking at systems that we want them to work for us, right? So as human beings from the early civilizations, we always wanted to make tools. We developed tools and developed everything. So we wanted the environment to work for us. Okay, we did not work for the environment. We try to make the environment work for us, right? So as such, right? As such, like that, right? So very simple idea. So the point being, for a mathematical modeling of a system, why do we develop a mathematical model? So that we can actually make that system work for us, right? Work for us. A very simple example would be, for example, a nuclear bomb, for example, right? So if you cannot control for example, you have nuclear fission or nuclear fusion, something like that. So if you have nuclear fission, which is the standard nuclear fission, right? So if you don't control nuclear fission, what happens? It becomes atom bomb, right? It destroys everything. But if you control nuclear fission, then what happens? You get a nuclear power plant, right? Nuclear power plant that does not pollute the environment, right? Like coal, like a thermal power plant. Thermal power plants are hugely responsible for polluting the environment. But if you can control nuclear fission, then what happens? Of course, you get a power plant. But if you don't control it, instead you get an atom bomb, which destroys millions of lives and everything, right? Things like that. So the point being, we want to control things to make it so that it actually works for us, not against us. Okay. So we look at systems we want to automatically control, and eventually what we do, we derive a mathematical model. Right? We derive a mathematical model. Right? So one of our teachers, so after becoming an engineer, actually after doing his master's degree, he joined a tea estate. So he's a pretty old person right now, and he joined a tea estate as a manager. Very surprising. Okay, and there he saw the interaction of different people with different people, right? How the entire thing. So for example, so how everything works. He saw that, and he developed a mathematical model of the economics that works inside tea gardens, for example, right? Tea factories, tea gardens. And later on, one of his students developed a huge and big mathematical model that can pretty much describe the economy of a country, for example. Okay, mathematically describe the economy of a country, how everything really works. Okay, so things like that. I did study that at some point. All right, so again, the thing is, I mean, we do not really need to develop mathematical model for everything, but we do often. So we developed a mathematical model, and now talking about mathematical model, what kind of mathematical tools do we have to develop a mathematical model? What kind of mathematical tools do we have? We have differential equations as mathematical tools. Okay, we have difference equations. We have integral transforms. So what are integral transforms? Integral transforms are Laplace transform, Fourier transform, etc. So example would be Laplace transform, Fourier transform. Then we have tools like linear algebra. Okay, we have tools like algebra. Now algebra is a very broad term. Ask a next time you see a mathematician, ask what is the definition of algebra. They'll probably smile at you and say nothing. So anyway, so these are the mathematical tools we have at our disposal, which, I mean, apart from many other tools, right? These are a few standard tools that we actually can use to develop a mathematical model. Once we are done with that, once we are done with developing a mathematical model, what we try to do, we try to make a mechanism to control that system, right? So we can use the mathematical model in two possible ways. One possible way would be to analyze. So we can use the mathematical model to analyze the system. Analyze the system for better understanding. Or we can directly approach this. So we can either analyze the system for better understanding using the mathematical model that we develop, or we can directly use that. So okay, we can either analyze the system for better understanding and then we can go to the next step, or we can directly go to the next step. Okay, and what is the next step? Make the system work for us. So that's, for our purpose, is making an automatic controller. Right? So that's kind of the purpose of an electrical engineer here in this. Any engineering purpose, right? So that's kind of our purpose here in this particular thing. So we look at something, we develop a mathematical model, then we can use the mathematical model to analyze the system for better understanding, and that could be the end of it. Or we can use that understanding to make the system work for us. So essentially here we could end from this point. We can just look at how the system works and end at there, or we can actually make a suitable controller and end there. So this is kind of the end of discussion. Okay, so that's kind of the entire cycle of things, rather, I would say, entire process rather. Okay, so now for classical control systems, we look at systems, for example, a mechanical system or an electrical system or a thermodynamic system, something. Okay, and we develop the differential equation model, something like that. Then we apply Laplace transforms or Fourier transforms or something like, again, linear algebra or something, right, to solve it. Okay, and then we develop a controller for our purpose, right? So we use a box like this. So this is again a very oversimplification of that, and this box would include a transfer function like this. Okay, and again, this is just an oversimplification, and the conditions under which the Laplace transforms exist you already know. The system has to be causal, linear, time invariant, single input, single output, with zero initial conditions. Continuous time also. Continuous time, causal. So again, continuous time, causal, linear, time invariant, single input, single output system with zero initial conditions. So you can understand that the conditions are way too many, right? So just to simplify things for an undergraduate student, so I would have the Laplace transform here, and this will interact with external signals. And since we are considering single input, single output systems, this will interact with a signal, for example, for which the Laplace transform is xs. Also, the output would be ys. But these are all the Laplace transforms, right? But we don't really want the Laplace transforms. We want to see, we know the signal in the time domain. It could be a step signal, it could be a ramp signal, it could be pulses, it could be other signals. But the point being, we know the signal in time domain, right? We would know the signal in time domain. Our objective would be to figure out the signal in the time domain, right? Our objective is to figure out the signal in time domain. But through the convolution property, we know that the output, the Laplace transform of the output of the signal is nothing but the product of the transfer function and the Laplace transform of the input of the signal. And what is the transfer function? We saw that in the last in the last class. The transfer function would be essentially the Laplace transform of the impulse response of the system. So this is kind of the procedure here. So we often have a system. Sorry, we had a intermittent network issue. Please refresh the stream. I think it will be fine now, right? So I think we are back. All right. Yeah, this happens sometimes. All right. Again, please refresh the stream. I would be waiting here for 1 minute. Right. As I was saying, we often have signals, rather, we would essentially know the inputs in the time domain, right? How they change with respect to time, and we would want to find the output also in time domain, right? So essentially, this would be the point. GS will be given, so the transfer function of the system will be given, or it could be derived mathematically, right, from the mathematical model of the system, right? And then, so that will be given. XS, which is the Laplace transform of the input signal, can be calculated. So if we know the input signal, we will be able to calculate the Laplace transform. Calculated. So YS can be calculated then just by multiplying XS and GS. Right? And then we can calculate YT by taking an inverse Laplace transform on YS, by taking an inverse Laplace transform on YS. So that gives me the output. So this is the output of the system. So that's kind of the objective here, right? Let me show you a very simple example. Simple example would be, say, I have a system for which the transfer function is 1 by s plus 1, say. And say the input is a unit step signal. I want to figure out the output, right? So what is my GS here? GS is 1 by s plus 1. What is XT? XT is the unit step signal. So what is then the Laplace transform of the input? That's 1 by s. We already know that. Again, we are talking about causal systems already, right? Then what is YS? So the Laplace transform of the output, that's going to be GS into XS. So GS into XS, that, okay, like that. Now we can use something. So this is like this is into S plus 1 by 1. Right? Now we can apply partial fractions, and I'm going to teach you how to better do partial fractions. Then if I do partial fractions, and if I write something like this, this is true, right? I mean, if you expand this in partial fractions, this will be the expansion. So this is my YS, right? Then what is YT? What is the output, right? That would be the inverse Laplace transform of YS. So that is the inverse Laplace transform 1 by s minus 1 by s plus 1. But how do I calculate the inverse Laplace transform? Not by integrating, but by figuring out whose Laplace transform is this one. So whose Laplace transform is 1 by s? Whose Laplace transform is 1 by s? So that's ut minus whose Laplace transform is 1 by s plus 1. That would be e to the power minus t ut. So that's the output then. So output is 1 minus e to the power minus t ut. That's the output. So this is kind of the way we actually derive this, right? That's very fine, right? So now if I ask you some very simple questions. So what if I ask you, what is the initial value of the output? So if I ask you what is the initial value of the output, what question am I asking? If I ask you what is the initial value of the output, question is, what am I asking really? Okay. If I ask you what is the initial value of the output, what I'm essentially asking you is that I want you to tell me the value of this when the system is just started, which means when I have just applied the input, what is the output? When I have just applied the input, what is the output? So this is what I'm asking. So when t is tending to 0 plus, so slightly higher than 0, right? Slightly higher than 0. So again, you can consider that 0 to be 0, for example. And if I put the value here, so this is going to be 1 here, this 1, this is 1 minus 0, so that 1 minus 1, so that's going to be 0. So this is the initial value of the output, right? That's fine. I could ask you another question, and this will be the question: what is the final value of the output? So final value means here I'm talking about the steady state value. So steady state means it has reached, so enough time has elapsed. Enough time has elapsed, and what is the final value of the output? So essentially what I'm looking for is limit t tending to positive infinity value of yt. So essentially this is often written as y infinity. Okay, so when time has elapsed, so when enough time has elapsed, so when t is positive infinity, so when a long time has passed, what is the output? Did the output settle down to a certain value? Okay, so we are looking for the steady state. So for example here, now what if I apply this? What if I apply t tending to my infinity here? So e to the power minus t, that will become 0. So this is 1, and subsequently the output would be 1. So I can ask you questions like this. I can ask you questions like this. But now, if my only goal is to know what is the initial output and what is the final output, so what is the output the moment I apply the input, and what is the output after a long time has passed? If these are my questions, if these are the only questions that I have, then I do not often need to calculate the inverse Laplace transform. Let me show you what I mean. For example, but consider this question. Consider this system. A system whose transfer function looks like right. And now if the input is unit step, the output is yt, of course. But my question is not exactly yt. I'm not asking you to calculate yt. Okay. Say my question is, so this is the input. My question is this. Okay. I don't. So for example, if I want you to calculate the output, for example, so what would you have to do? You would have to take the Laplace transform here. That would be 1 by s. Multiply with this entire thing here. Okay, and do a partial fraction using any suitable method if possible, and then you have to take an inverse Laplace transform. I mean, this is easily possible with a computer, but doing that manually is difficult. But what if my question is, what are the initial and final values of the output? What if I'm asking what are the initial values and the final values of the output? So what if I'm asking, right after applying the input, what is the output? And when the system is running for a long time, what is the output? If I'm asking these questions, then we do not really need to take the Laplace transform, do not really need to do all the computation, right? So under these scenarios, if I'm asking you these questions only, what is the output initially and what is the output finally, so after a very long time, right? Then if I'm asking you these questions, then it is not always necessary to calculate the inverse Laplace transform and all, right? We can use two very important properties of Laplace transform, namely the initial value theorem and the final value theorem, to actually get to that one. So this is the thing that I am going to derive right now. So let's start with the final value theorem. Okay, so the final value theorem. The point being, the question is, so final value theorem, my objective is this. Okay, my objective is this. We know that the Laplace transform of yt is ys. So we are trying to figure out what is the value of the so essentially we are trying to figure this out without calculating the inverse Laplace transform. So essentially point is we are trying to figure this out without calculating. So this is y infinity, right? So we are trying to figure this out, right? The point being we want to calculate this value, so essentially this limit without doing an inverse Laplace transform, doing an inverse Laplace transform on ys, right? Essentially without doing an inverse Laplace transform on ys, what if I want to calculate this, right? What if I want to calculate this value? So let's see. Recall the derivative property. Moments ago I told you. So let's figure out what we are trying to say. Recall the derivative property. We know that from the derivative property, from the time differentiation property, we know that the Laplace transform of that time derivative of xt, what is that? That would be xss minus x0. All right. All right. So we know that. Fine. So what is the definition then? By definition, what we are calculating here is 0 to infinity. Again, we are considering causal systems. So we are considering causal systems, right? Of course, this came from a causal signal. So yt is causal. That's one of the assumptions here. So again, instead of writing xt, I'm writing y here. So instead of doing that, I'm writing this, and I'm writing this, of course. And by definition, I know that this is y dot t e to the power minus st dt. Okay, and this is pretty much whatever we're going to derive here would be valid for any other signal under certain conditions. Of course, we are going to see that. So that is ys minus y0. Again, this is the Laplace transform version, and here this is the initial condition. Right. Now with this equation, let's apply a limit on both sides. Okay, let's apply a limit on both sides. So here I'm writing limit s tending to 0. So I'm applying a limit on both sides. I'm saying limit s tending to 0 here, and of course the integration is this. See what I'm trying to achieve here. Again, this limit won't directly affect the integral because the integral is with respect to t. Right. That's fine. Now look at this integral here. So if s is tending to 0, which is a very small quantity, okay, say 0, then e to the power minus st will become e to the power 0, which is essentially 1. So if I take care of the limit, then this becomes integration from 0 to infinity on y dot t dt, right? All right. So with this said, now look at the right hand side. So this portion is a function of s. So I'm writing limit s tending to 0 s ys minus, now this portion is independent of s because that's a constant, that's the initial value of the output, right? Initial value of the output, so that's y0, right? Right. So now what about this integral? So this is the integration of the derivative of yt. So what is the integration of derivative of yt? That's just yt, right? So this is the integration of derivative of yt, that's just yt. Limits are from 0 to infinity, and that's going to be limit s tending to 0 s ys must be minus y0. All right, all right. So now of course let's put the limits. So that's going to be y infinity minus y0, and we have limit s tending to 0 sys minus y0. Notice that this limit is only on sys, okay, because this is a constant. Since these two terms are finite, they can cancel out from each side, right? So what we essentially have is y infinity to be equal to limit s tending to 0 s y s, right? So let me go back and write it down here, is that this is equal to limit s tending to 0 s y s, right? I'm going to tell you what is the significance of this, but before I do that, let me tell you that there is a significant condition here. The condition is that this limit must exist. What is the condition here? Condition is that y infinity must exist, right? So y infinity should be bounded and should be non-oscillatory, should be finite for that matter. So, and who would ensure that? So we will later on see that this condition is ensured, okay, this condition is ensured if the system is stable and the input is bounded. So just keep that in mind, okay? So these are the two conditions that must be satisfied for this. The system we are talking about should be stable and the input that we are talking about must be bounded. Under these conditions, y infinity, this limit would exist, and I'm going to explain this at a later class, okay? And under these conditions, y infinity would be finite and it would exist, this limit would exist, and subsequently this derivation would be true, fine. So right, so this is the proof of this, proof of the final value theorem. But let's use this theorem to for this problem here, okay? Now let's use this theorem for this problem. So let's consider the example once again. So that was our system, okay? So now this was the unit step signal. So right, okay, so input is the unit step signal ut. Then what is the Laplace transform of the input? That's 1 by s. What is the Laplace transform of the output? The Laplace transform of the output is of course gs multiplied by xs. So that's going to be this multiplied by 1 by s. So subsequently, if I just copy and paste, which apparently I cannot do. Okay, and of course this is into 1 by s. So essentially, so s multiplied by this, right? So this is the Laplace transform of the output. So what if I want the so if I want yt, so that would be the inverse Laplace transform of this entire expression here. And of course, in order to do the inverse Laplace transform, we would need to convert this into suitable partial fractions and then figure out whose Laplace transform is this, whose Laplace transform is this, and subsequently do that, or use a computer, okay, things like that. But what if my question is not, what if I'm not asking about yt? What if, but what if I am only interested at knowing the output at t tending to infinity. So what if I am interested about the output at steady state? Again, I am throwing around the word steady state. This steady state phrase will be explained properly in our discussion on stability. So what if I'm only interested about that? Do I still have to use the Laplace transform? Inverse Laplace transform? No, I don't have to use the inverse Laplace transform. So there are two conditions I must satisfy. I have to make sure that the input is that the transfer function is stable. I know this transfer function is stable, and later on you shall also know that this transfer function is stable. But for the moment, just remember that this transfer function is stable. Okay, so you will know why later. Why? How do I know that this system is stable? You would know why. You would know how later on. Okay, not now, but later on you will know. Okay, and input is bounded, right? Xt is bounded. Bounded means the input does not go to infinity. You already know how, because that was a step signal, right? Step signal does not go to infinity. It's a bounded signal, right? If it was a ramp signal, it would have been an unbounded signal, right? So under these conditions, I can apply the final value theorem. So what I'm looking for is y infinity. So the output in the steady state, which is essentially the limit of yt when time goes to infinity. But what is essentially this one. Now using the final value theorem, I can say this is also equal to the limit s tending to 0 s fs. Sorry, s ys, right? So what it means is that I can calculate the output. Again, look very carefully. This is in small letter, right? This is lowercase. So this is the time domain output, right? And this is the Laplace transform of the output. I can calculate this limit, and this will give me the output when t is infinity. Of course, if these two conditions are satisfied, which are being satisfied at this moment. So what I am essentially calculating right now is limit s tending to 0 s into ys, and I already know the value of ys. So what is ys? The Laplace transform of the output, which was this one. So if I calculate this limit now, I would get the output in the steady state. What is the output of the value? So when the system is running for a very long time, what is the output? Now let's apply our ideas of limit. Again, let's apply our ideas of limit here. So before doing that, let's figure out that this s can be cancelled here. Okay, they are getting just multiplied here. Okay, and we are kind of left with limit s tending to 0. We have 3s square plus 5s plus 23 and 9s square plus 7s plus 19, right? And we are just calculating limit s tending to 0. This is finite. Both the numerator and the denominator are finite. So we can just take the ratio of the finite limits of individual here, right? So whenever we are taking a limit of a quotient, okay, if the numerator and the denominator are individually finite, we can just take the limits on the numerator and the denominator and divide them. So the limit of the numerator is, by putting s equal to 0, it's 23, and the limit in the denominator is 19. So the output is 23 by 19. So what I essentially have is that y infinity, so the steady state output is 23 by 19. But look carefully, we did not do an inverse Laplace transform. So if you're just interested about the initial value of the output or the final value of the output or both, instead of calculating everything, all the inverse Laplace transform and everything, instead of going through all the hoops, we can just apply the final value theorem and the initial value theorem accordingly to calculate those values. But for final value theorem, these two conditions must be satisfied. Just keep that in mind. These two are very important conditions. Unless these two are satisfied, the final value theorem is not applicable. Okay. These two are necessary and sufficient conditions for the applicability of final value theorem. With that said, let's go to the initial value theorem, and we would have a same structure here. Okay, same point of thinking here. If just like this one, same point of thinking is that if I am interested about the initial value of the output, okay, so I have a system on which I have applied an input, and I want to figure out what is the output just after the application of the input. So I have a system, I just applied an input, and right after applying the input, what is the output? If I am interested about that, okay, then we need to use the initial value theorem. And of course, if you want to skip the inverse Laplace transform, if I could calculate the inverse Laplace transform, very well, you can just put the limits on the inverse Laplace transform itself, right? That would do. But here is the initial value theorem. So which essentially we are calculating this limit essentially. So we are calculating y 0 plus, which is again essentially limit of yt when time is 0 plus. Now what is this 0? Okay, someone is asking what if, so I understand your question. What if I want to find out this? Something like this. Let's say for example at t equal to 1 second. What if I want to find out this? What if I want to find out this? Now there is a very interesting thing, because let me just explain this first. Okay, let me explain this first, then I am going to come back to your question. But your question is pretty fantastic here. What if I want to figure out the output at a certain instant? And this can be still done using the initial value theorem. You will see why. Okay, because the system is time invariant. Because of that, we will be able to do this. Because the system is time invariant, simply because of that, we will be able to actually calculate that. All right. Now, again, the better option would be to actually do the integration and accordingly calculate everything and subsequently find the values and such and such. Right. But when the signal is applied, if the signal is applied at a certain point, we will be able to know that. Let's see. Okay, all right. So again, look at this one. Okay. So now let's figure this out. I do not know what about this one. Right. So let's see. Again, recall. Recall the time derivative property, that the Laplace transform of the time derivative of a signal is xs minus x0, right? Now here we are saying that instead of writing x0, I will be writing 0 plus here, which indicates, again, not x, right? Let me just show you what I mean. This would indicate that, fine, I am looking at y equal to 0, looking at time t equal to 0, but just right after that. Okay, since this yt signal is continuous at t equal to 0, probably, then this would be valid, right? So again, because of the continuity property. Okay, right. Given that. So with that said, what is the definition of this? Again, the definition is again yt is causal, so 0 to infinity, so y dot that t e to the power minus st dt. For a causal signal, the derivative is also causal, of course. Because of that, we have this. So just keep that in mind. 0 plus means right after 0 for engineers. For mathematicians, we are actually approaching on the time axis from positive infinity to 0. We are approaching 0 from the right hand side, essentially. Forget that. Anyway, so we have this expression. Now, what if I apply limit s tending to infinity on both sides? So essentially what I mean, what if I want to apply this limit on both sides, essentially on this and also on this. So I have sys minus y0 plus. Again, look very carefully that this limit is only applying on this one, right? Only getting applied on this one, because this is a constant as far as the limit itself goes, because this is the function of s and the limit is on s, and since this is a constant, also it was a function of time. So this is on this, the limit is not being applied, right? Very simple. That's the constant factor being subtracted. Now what if I put s equal to infinity? So if s is equal to infinity, then this is e to the power minus infinity, no questions about that, right? So this is e to the power minus infinity, right? Got it? So if this is e to the power minus infinity, then this is 0, right? If s is infinity, so then this is e to the power minus infinity, then this is 0. So this entire left hand side is 0, right? No conditions here. This is always 0 as long as t is positive, and which it is, t is positive, then of course putting s equal to infinity, I mean, a very large value for infinity, that would make e to the power minus st equal to 0. So the left hand side is always 0. So I have limit s tending to 0, so s tending to infinity, s ys minus y0 plus. So essentially if I bring this one to the left hand side, so I would have y0 plus equal to limit s tending to infinity s ys. So let me just write it down here. So limit s tending to infinity s ys. Okay, and this is the proof of this. So now with this, let's go back to the previous example where we were actually applying this. Let's imagine we have again this same example setting here. Let's use the same exemplary setting here. Say we have this system, we have the same input, okay, and we want to calculate, we want to find the output just after applying the input. So this is the output just after applying the input, right? So this is the output just after applying the input. So of course we know that ys would be gs into xs, and xs was 1 by s, gs is known, the product is also known, gs into xs was this one, right? So this was gs into xs. This entire thing was gs into xs, right? So this 3s square plus 5s plus 23 divided by 9s square plus 7s plus 19, that was gs, and xs was 1 by s, so that is getting multiplied here. All right. So let's just write 1 by s. So instead of calculating the inverse Laplace transform to find the limit, we can apply the initial value theorem, and initial value theorem does not have any condition as such. Okay, so no conditions required. You can just blindly apply initial value condition, it will be fine. Okay, as long as the system and the signals are causal, otherwise things won't work. So causality is the only condition here. Condition is causality. Let me just write down yt is causal. So condition is that yt is causal. There is no other condition. Hold on, did I write the condition? Yt is, so here the condition is yt is causal, and also these conditions, right? Right, and okay, right, these are the conditions. Just keep that in mind. There are so many things here. So here the only condition is that yt must be causal. Okay. Under that condition, of course, so yt is of course causal, right? So we are now trying to find out y 0 plus. So this is the output right after the application of the input. So this can be done by calculating this limit s tending to infinity s ys. So limit s tending to infinity s into right. So I can cancel this out, cancel this out. Of course, the same thing is happening here. Now s tending to infinity, how do you apply a limit tending to infinity? Okay, now here the point being, the numerator and the denominator is not directly having a finite value if I put s tending to infinity. Okay, so what we instead do, we divide. So this is how we calculate the limit for infinity, limit at infinity, when the numerator and the denominator are polynomials. So what we essentially do, we divide the numerator and the denominator by the highest coefficient, highest order coefficient of the polynomial. So here, what is the order of the polynomial in the numerator? 2. What is the order of the polynomial in the denominator? 2. So what is the highest order? 2. Okay, so you divide everything by s square. If the highest order was 3, we would divide everything by s cube. So here I'm dividing the numerator and the denominator by s square. So I would have 3 plus 5 by s plus 23 by s square. And here I have 9 plus 7 by s plus 19 by s square. Someone is asking a question. You could apply L'Hopital's rule. That would also do. You'd have to apply L'Hopital's rule twice here. Right? Yeah. And I'm quite impressed that you said the name of the person correctly. So it is L, not L Hospital. Okay, it is L'Hopital. I'm not applying this rule here. Right? It's a very simple one. All right. Now, of course, now the limit can be calculated very easily, right? So of course, now if s is going to infinity, then look at the numerator. This 5 by s will be 0. This 23 by s square will also be 0. This s 7 by s will be 0, and this 19 by s square will also be 0, right? So I would have limit. So essentially, after putting the limit, this will be 0, 0, 0, 0. So I would have 3 by 9. So essentially, that's 1 by 3. All right. So the initial value of the output would be 1 by 3. So we calculated the initial value of the output and the final value of the output without actually ever calculating the inverse Laplace transform of the system. So these are two of the very important properties of Laplace transform here, right? So the initial, rather very important theorems. These are strictly speaking not properties, because we derived everything based on our definition of the Laplace transform of time derivatives. But nonetheless, these are really important, right? Right. All right. And there is just one more for you today, and which will be the time integration property. So all right, so let's, okay, maybe we shall be doing the time integration later on the next one. On the next one, we shall leave time integration. We shall leave frequency differentiation. All right, that can be done. Yes, fine. So let it be. Let's stop here at this point, and that's the end of the discussion today. So feel free to ask any question that you probably would have. So this was kind of a long discussion today. Fine. Can anybody? So if you have any query, feel free to ask. Otherwise, we are going to end our stream today. So the first assignment, if you're talking about the first assignment, so just go to the assignment section. Let me show you on Google Classroom. Hold on for a second. So Let me just switch the view. Okay, so this was the our Google Classroom here for control system theory. So if you go there, and you can find it from the front page of that, if you say so, or you can go to the classwork. If you're looking at the front page, you can see there is a new assignment. Okay, or if you can go to the class, if you go to the classwork, you will see there is an assignment here. Just go to the classwork here and click on that. So assignment here. So you will see that it is saying that it is due on 16th September. So is it feasible? Right? So it is due on 16th September as it can be seen. Right? And of course you can download the copy file here. Okay, and of course these are on block diagram reduction and signal flow graphs. Okay, of course I think we did problem number 1 and problem number 2 in our earlier classes during the streams, right? Problem number 3 and 4 will really be the exercises, and for problem number 5 you don't have to do block diagram reduction, you just need to do the signal flow graph, because this is one of the examples where you would see the power of signal flow graphs. I mean, doing a block diagram reduction on this would take a lot of headache. And just one more thing, a pro tip, simply don't write GS, you just write G1, G2 and like that, skip the S. Okay, it is understood that transfer functions are functions of S, so you don't have to write GS, HS like that, just write G1, G2, this will be fine. G1, G2, H1, H2 like that. Okay, so yeah, that would be the thing. All right, and of course if you are trying to figure it out from the front page, you can go to the stream, and here sorry, not this one, on the stream, if you are clicking on this one, okay, you would see an assignment here, and with that said, if you go to the instructions section, okay, you would end up with the same result. All right, so with that said, yeah, all the homeworks will be posted here, and you are required to post your answers on Google Classroom, right? Because managing emails is a very difficult, becoming a more and more difficult task. Anyway, thank you very much, and I will see you tomorrow with Python programming. So tomorrow in Python programming, we shall be seeing how we actually can use our knowledge that we gathered so far to do plotting, because as engineers, doing plotting of different signals and graphs and everything is kind of one of the important tasks, right? To visualization, we're going to look into Python visualizations using Matplotlib. So thanks for joining me, and I'll see you tomorrow. Again, if you have any query, just drop me an email. All right, so thank you for being here. I'll see you tomorrow.